Hey everybody, it's Ripley. I'm back again. We're going to talk a little bit about vectors today. Okay, now vectors are a little bit tricky, but they're really not all that bad. All that they really are is what's called a directed line segment. Directed line segment. Okay, and it looks like this. So this would be an example of a vector. So it's a line segment, but it's got a direction to it. And so it starts at a point and it finishes at a point. Now, sometimes this is people will erroneously refer to this as a ray. It's not a ray, because in the geometric context, a ray goes forever. This thing has a starting point and it has a finishing point. Now, the most important thing about a vector, what makes it a vector, is, like I said, it's just a mathematical mathematical construct, too much caffeine at lunch, that has direction, and magnitude, magnitude. All right. In other words, it has a length and it has a specific direction. So that brings up interesting points. Sometimes it's really nice to use graph paper for these types of displays. Watch this. So I'll have a student ask me, Ripley, if I create an array that starts at the origin, it's just begging to be put on the origin, right? And it finishes, so this thing starts at 0, 0, and it finishes at 0 or at 3, 0. Is that the same ray as one that, say, starts here at 0, 2 and it finishes at 0, 5? Are those the same? This is 0, 5. Are those the same vector? No, they're not. They have the same length, right? They have the same magnitude. The magnitude in both cases, this has a magnitude of 3 and this has a magnitude of 3. But they have different directions. Now, how about this guy? What if I put a vector up here that starts at, say, 2, 3, and it finishes out here at 2, 6? Well, 1, 2, 3. Wow, I'm kind of jammed in here, aren't I? At 2, 6. I need to do a little erasing here. Pardon me, guys. So if I erase this little chunquito right here, and I put 2, 3 here, and 2, 6 over here, is that the same vector as this guy right here? Well, does it have the same length? Yes. Does it have the same direction? Yes. All right? So it is exactly the same vector. So now that tells us a really important little lesson. I can move vectors all over the place. I can move them wherever I want them to be, and we're going to use that tool over and over and over again. Now, often, when you first get introduced to these, and you'll see this sometimes in physics as well, what you'll have is you'll have a vector that starts at some point P and it finishes at some point out here, say Q. All right? And this will be referred to as PQ notationally. Now, this is one of those crazy mathematical constructs, like I said, where a lot of different people have worked on it over the course of time, and they've come up with different notations. So you'll see this vector written as PQ. However, mathematicians, you know how we are, we don't really care about any fancy notation. So what we're just going to do, we're going to give it a name, like Bill or Bob or, say, V. So we're going to call the vector V. They are exactly the same. There's no difference between vector PQ and V except notational, of course. Now, think about this for a second. This is always fun to sort of wrap your brain around. If this is V, now remember, I said I could move vectors wherever I wanted, right? So if I wanted to, I could take V and I could stick it so that the initial point, let's talk about this. This is called an initial point, and this is called the terminal point. All right? Because this is where it starts and this is where it finishes. And you may say, well, Ripley, does it matter? Well, answer your own question. Look, if I start at Q, I'm going to just lay this right over the top, and I finish at P, is that V? Think about that. Is it the same length? Yes. Is it the same direction? Is the arrow headed in the same direction? No. So the answer to that is it's not V. Well, if it's not V, what is it? It's negative V. Think about it like wind. If you're standing in the middle of your yard and the wind is blowing with a certain force. Vectors very often are used to denote force. Excuse me. Wind is blowing with a certain force, right? If the wind changes directions exactly opposite, it has the same force, but it's blowing in a different direction. So it's going to have different effects on things like birds trying to fly around in the yard or planes flying in the sky, right? At the very simplest, think about it this way. If you've got a, oh wow, you guys get to see me try and just butcher what a plane looks like. All right, here's a plane, right? Just shut it. I know all of you are laughing right now, and that's just cruel. A plane is flying, okay, in this direction. If I have a 35-mile-an-hour headwind, that means, think about the effect. This is going to be 35 miles an hour. Think about the effect on the plane. It's going to slow the plane down by 35 miles an hour, right? If I have a 35-mile-an-hour tailwind, 35 miles an hour, what's going to happen? It's going to speed it up. Now, 35 miles an hour is exactly the same speed, right? The same velocity. It just has a different effect on the plane. So they can't be the same vector because that force is acting on the plane. So if I name this guy v, then this guy is going to be negative v. Same force, same length, same magnitude, opposite directions. All right? Now, let's talk a little bit, excuse me, really quick about adding vectors. All right? Typically when we talk about vectors, we have two names for them. We call them v and w. Vectors? Wow. Let's see. Adding vectors. Adding vectors. All right, I'm going to add v and w. So what does that mean? V plus w. All right, now watch how this works. This is kind of cool. Let's make up a couple of vectors. I'm going to set one here, and I'm going to move it over. Let's have it finish right there at this point right here. And I'm going to name this v. Okay, and then I'm going to have one start, let's say here, go away. Let's not go away. Let's use different colors. All right, I'm going to have one here, and I'm going to have it finish right there. So it starts here, and it finishes here. And this guy's going to be W. Now watch this. If I add them, the way that I do is I take, you ready? I take the tail of the second vector and attach it to the head of the first then connect the tail of the first, the tail of the first to the head of the second, to the head of second, and that is your sum. Now let me explain this. Let me walk this through. Remember, vectors are mobile. I can move them wherever I want. So what I'm going to do is I'm going to take W and I'm going to slide him over here. Now look close. I went down 2 and over 2. So I'm going to connect it right there, and I'm going to go down 2 and over 1, 2. So remember, I can move them wherever I want. So here's W, and then what I'm going to do is I take the tail of the first and attach it to the head of the second. All right, now so what I do is I go tail to tail and head to head. This is V plus W. Now this brings up an interesting point. Is V plus W, change colors again, I love having colored pens for vectors, is it equal to W plus V? Well, W plus V. So what would I do? Let's see, what did I do? I went up 2, 1, 2, and over 1, 2, 3, 4, 5, 6 to get V, right? So if I go W plus V, I start with W, and then I grab V, and I attach it to I take the tail of the second, which in this case is V, and then I go up 1, 2, and over, what do we say again? 1, 2, 3, 4, 5, 6. So over, up to 1, 2, 3, 4, 5, 6. Right? And right there is V, so W plus V, and the resulting vector is, look at this. Well, badly drawn, sorry guys, badly drawn, and this is W plus V. Now look close, look at this. V plus W didn't rise at all, right? So its direction would be like a 0-degree direction if you think about it. And I just go over 1, 2, 3, 4, 5, 6, 7, 8, and let's look here. If I start here, remember, tail to tail, head to head, and I count over 1, 2, 3, 4, 5, 6, 7, 8. They are exactly the same vector. They have the same length. They have the exact same direction. So guess what we have? We have a commutative property. Now let's do v minus w. Real quick, I got to change colors because this is really the most important part. If you can visualize this, you'll understand what's going on. Well, the first thing, oh wait, let me slow down a little bit. I want to make sure that I mentioned what we just proved. This is a yes, and we just proved the commutativity of addition of vectors. So watch how this works. We're going to do v minus w. So I'm not going to think of this as v minus w, but v plus negative w. Okay, so let's do our v again. Here's my v, and I'm going to go up 2, and what I say, 1, 2, 3, 4, 5, 6. So there's my finishing point. I'm going to name this guy v. And then I'm going to stick w over here. That's just for fun. I'm going to move it around. Let's put it right. Remember, I'm allowed to put them wherever I want. So v, oh, no. I'm going to need a little more space. Sorry, you guys. I'm going to need a little more space. So I'm going to call this guy right here. We're going to do, this is w. Now the question is, what is negative w? Well, let's change colors again. Negative w is the exact same length, but in exactly the opposite direction. So this guy right here is negative w. So if I'm simply doing v plus negative w, then, sorry, I'm going to fill this in here, then all I'm going to do is I'm going to take this vector right here, and I'm allowed to move them all over the place. When I don't want it to work, it works, and when I want it to work, it doesn't. So I just move negative w up here. Remember, I take the tail of the second, attach it to the head of the first, right? And then I do there. So there's negative w, and the resulting vector is tail to tail, head to head. This right here is v minus w, right? Now, remember, this guy right here was negative w, and this guy right here is v minus w. That's pretty awesome, isn't it? That's very powerful, and you're going to get tons of practice at adding and subtracting these vectors. Okay? Now, let's talk a little bit about properties of vectors.